Well, welcome back. Today's task is not to chase a rainbow, but to chase this rainbow away. This is our color lock, and it's not working. So I've been looking at all of the various vital functions in the color circuit. I have to admit I didn't know that much about it, so put some time into this. What we have here is the positive and negative going burst signals from the discriminator circuit, and they're in sync, so that's right. And there's a couple of other things that we're looking at. So we've got well, you can just see where we're tacked in, and we'll show that schematically. But that's the positive and negative side of the phase detector in part of the color circuit, the discriminator. And we are on color bars here, channel 5. The set still is not starting up smoothly. We got to do a lot of channel jiggling to get it to come on, but let's take a look at a vital function and then we'll go to the schematic. I've got our VTVM set at a volt and a half scale. So right about there is 1 volt, and got our probe set on DC. And this red test lead goes back here. I got to be careful the set is on, but right there you can see the test lead. The red test lead goes into a point that is called test point W, as per the Zenith schematic. All right, so I'm clipped in on the voltmeter to test point W, and it's pinning the meter. Now, in our setup procedures, Zenith says go to a point in between channels where there's nothing. No signal condition is what they call it. And this burst we're looking at right here is our free-running crystal oscillator. So right up here, that crystal is functioning, so that's good. And down here it's curious. I've been observing this for a little while, how test point W is wavering, and I'll show you on the schematic what that means. Sometimes it's been even wavering up to over a volt, which is exactly what we don't want. But let's take a look at this voltage. If we disconnect this, white lead is point K, test point K, which is the color killer. So when you ground test point K, it activates the color circuit, bypasses the color killer. So at this point we have this voltage at test point W is wandering plus and minus a volt. And that's not good. And I wanted to show you another thing. Let's turn our other meter on, and I believe we're clipped in we're clipped into the chassis. So I wanted to show you what happens here at this resistor, the point on this resistor and the point at this resistor over here. It is a discriminator circuit, a pair of 2.2 mega ohm resistors. So this is one side of the burst discriminator. We have, hard to see, minus 23, 24 volts. That's at one side of its maximum. And then this point here is on the other side of the discriminator. And we have a considerably different reading, 14 volts. So again, the first side that we looked at is a negative voltage, and the other side is a positive voltage. Right now we're looking at our free-running burst crystal oscillator and the differential voltage at test point W. And the Zenith schematic says that a normally functioning color set should have almost nearly 0 volts at this point. So things are in question. So let's shut it down. And we'll look at our schematics. Well, over here on the table, I've joked around a little bit, half serious, half joking, that this is like the Rosetta Stone. This is the Zenith schematic. This is the SAM schematic of the same chassis. So you have the same story being told, but you have two completely different languages. And I still find it fascinating how you can take the same electrical diagram and draw it much differently, interpret it different ways, but they all do the same thing. They go to the same spot. So for the sake of the argument today, I think we're going to take the SAM's schematic, which I normally prefer, and we're going to put this off to the side because I think the section of the schematic that we're interested in kind of studying is this one. This is the discriminator that we were just looking at. So our scope probe leads were attached here and here. And this is the burst amp down here. This is the reaction control, and that's the crystal oscillator. People talk about it being 3.58, but it's actually a rounded up number. It's 3.5795 something. So, but the oscillator works fine. And these reaction controls, these two coils, control the frequency and the amplitude. And this test point W we were clipped into to read the voltages right here. And that essentially is at the center point, the center tap of this voltage divider and phase detector. So we should see 0 volts right there where we were clipped into that red lead. And we didn't. We had a voltage present. So that, and we looked at, with our other meter, we looked at this point here. I think we had a minus 24 volts at this point, and then up here we had like 14. So that's a pretty significant difference. They're not balanced, and we need to look into that. So that was our first instruction right off the bat, was what is that voltage right there? And down here is our burst amp. We were looking at, at one point the free running crystal. And then with a signal applied, we were looking at the actual burst amp. And we did not look at this point, the burst takeoff, but let's look at something else and I'll tell you about that. Well, I've been doing a lot of reading, and these are the two main things that I've been looking at. And this is a really well-known book, Basic Television by Bernard Grob. This is the 4th edition, 1974, something like that. A book like this, with the title of Basic Anything, is an oxymoron. This would be like a book called Basic Calculus or Basic Brain Surgery or something like that. I didn't find anything basic about this, but it is chock full of all the wisdom of television, so you just have to be patient and plow through it. And then this book is sort of a well-known book. the Zenith Color TV Service Manual, and it's written by a guy named R.L. Goodman, if you can see that. And these two books are available on eBay and stuff like that. And I'd say if you are, well, they're pretty essential. I learned so much about the color sync and burst in this book and in this book. And if this presentation sounds like it's filled with unorganized description, it's because I'm still trying to figure this whole thing out myself. But let's start here. The R.L. Goodman book. And here we have our chapter on chroma and video circuit troubleshooting. And let's just start with what we just did, the sentence about that. In a properly operating Zenith color set, the voltage at test point W will generally read about 0 volts, 0 voltage, when measured with a VTVM under no signal conditions. And that means the tuner is set between channels. Should this voltage exceed 1 volt, positive or negative, several different color picture symptoms may appear as follows. And then it lists a bunch of different things. And then on the following page, it talks about what some of the causes could be if you have the presence of a voltage that's greater than and less than 1 volt. So that's all super good. And I stared at I thoroughly read this chapter, and I got stuck in it for an hour. I just couldn't figure out what the hell they're talking about. And there's a reason. So let's start with the reason. It refers in this text that this is going to be, there is a schematic right here, that this schematic right here, the schematic for the Zenith 20Y1C38 on the next page, figure 3.3-1, is the one that they're going to refer to. So there's a description of the circuit based on this schematic right here. And then they have, in that description, there are screenshots off of an oscilloscope that tell you what you should and shouldn't see. Now, there's a lot of reference to coil numbers, L44, and wait a minute, that's not L44, what? So I stared at this, and I was trying to follow the circuit description, and follow the schematic, and follow the waveform snapshots and the captions, until about an hour later, I realized that this is the wrong schematic, and these pictures are not in the right place relative to the captions. So, word of warning, I don't know about the rest of this book, but the information is solid, super good, but it's badly out of order as a publishing thing. So, a few pages down here is the proper schematic. It says this is the 14Z8C50. It is not. This is the schematic that should be in the front, and this schematic should be that one. So this chassis that they're referring to in the text should be a 20Y1C38. Now that chassis, I just know, didn't have an IC. But the chassis that they are referring to in this, this schematic, this one, should have an IC up here in the color demodulator, and it doesn't. So it just took me a minute. Then I started looking at these coil designations, L44, and the reactance is, well, it's not, this is not our chassis, but it was just referring to circuit description. So, and then, well, going back to this caption belongs to this picture, and this caption belongs to this picture. And once I figured that out, then the light bulb came on. It took a while to figure that out, and I don't know, maybe that's the ultimate test. That was the test. That rant was just about beware. When you have these technical descriptions and the schematics are the wrong ones and the captions are not related to the images, you just chase your tail when you don't know. And it just took a long time for me to figure this out, because this one referred to a dual wave, and this is a dual wave, and then this caption said, here is the burst riding on the side of the king pulse, and that is the description. The burst is riding on one side of the king pulse. So the in broadcast television, what used to be broadcast television, Bernard Graab was telling us about this, that the burst signal is on the back porch of the horizontal sync pulse. So each scan line has a burst that has 8 to 11 separate bursts of the 3.58 color subcarrier. And you need that, so when that's active, it comes over here and it eventually mates up at this point with our free-running oscillator, and they synchronize themselves and allow the color to lock. So without the presence of burst in the transmission, it would show a voltage over here. So we have two things going on. This discriminator circuit, one works the automatic color control, or the color killer. So without the presence of burst in the transmission, that would simply be a black and white picture, because there's no burst in a black and white picture. It would shut the color circuit off so that it didn't have a color rainbow around the edges of things. So, you know, if you're going to watch a black and white movie on your old color TV, I turn the color killer circuit off, and when I watch a color movie, it's got to be on. So that's one thing to talk about. So the color killer is one discriminator circuit, and this does seem to be okay. And this one mates our color burst that's in the signal with our free-running oscillator, crystal oscillator, and that's where this disparate voltage comes from, and we have color sync based on that. This up here is a phase changing network for the blue minus luminance and red minus luminance, but that's another thing. So we're just looking at this discriminator right here, and this. Well, this is our discriminator circuit, and let me show you. This resistor and this resistor are the two in question, and then these are the diodes in the circuit, and then this resistor, this one, and these two diodes feed the ACC killer circuit. So right now we're going to look at this one and that one. So that's the common point between the two resistors, and then at the bottom of them, where they join up with those dual capacitors, that's the other side of the phase detector, and then the two center leads from that capacitor, those capacitors go into that coil right there in the middle. So let me just show you what they are on the schematic. So that's where we're tied. So this side of these two resistors are bridged with that purple wire. And then that purple wire goes up to this coil resistor and into the grid of the 6GH8, the reactance controller. So we are clipped in with our meter right there, and then we'll just read either side. Well, those are the diodes. But we're clipped into our meter right there, and then we'll just read either side of these resistors, and we'll know if they match 2%. So here on our fancy pants meter, we're just gonna take a look at them real quick. We're clipped in here. Purple wire goes up to the 6GH8 oscillator crystal tuning coil, back down here. So one side of the resistor, the other side of the resistor, or this is the common point of the resistors. So this is one side here, and we have 1.76 megs. Well, that's lost value. And then over here, the other side of the discriminator, look at that, 2.3 megs. So that's 300,000 plus 300,000. That's like 600,000 ohms off between the two. And the only way to really confirm that is to take them out of circuit somewhere. Snip them, and if you do that, you might as well just replace them. So, like we suspected, they don't match, at least while they're in circuit. So we have to take them out, lift them out of circuit in order to confirm that. So I'm going to snip these things, and at that point, if we snip it, I want to make sure that I leave enough lead to test the resistor, but also enough lead to make a little hook and solder something else in its place. Because at this point, if we snip one side out, there isn't really enough lead to hook it back together and solder it, I don't think. And I think so what we're going to do is something like this. Snip, so there's enough lead to test it and enough lead to hook it. And then over here I'm going to do, there's this capacitor that's right in the way, but I'm going to do the same thing. Snip. All right, so we have I have this. All right, I'm going to put this cap. This lead will have a hook on it, and before we snip the other end, we're going to test these leads, these resistors, on the leads that are there. All right. So let's do this. Clipping lead there. Turning on our meter to resistance. And what do we have here? 2.38 ohms. 2.38 mega ohms. And what about here? 2.37 mega ohms. Well, these resistors are fine. I don't know what to think at this point. I'm surprised there is something in this circuit that would have taken each side in such a different direction. Obviously that's going too far. I mean, the 0 beat pattern is right there, but we're not anywhere close to being. What if we just go wacky? Are we getting more lines? See that? Yes, we're getting more lines. We want fewer lines. Now we start turning it in the other direction, and it's picking up frequency out of sync in the other direction. Wait a minute, we're getting closer. I think. All right, I've reached the end of how far I can turn that core, and it doesn't look like that. It looks horrible by eye. No way, Jose. There's something so messed up here. This doesn't make sense to me. Something else is going on in this sync circuit. That's kind of back to where we were. Alright, so that doesn't work. We can't get there turning the slug that is the frequency adjustment. And I really hesitate fooling with this one. So if we were going to fool with this, we have our VTVM. That's a 4.7 meg resistor that they tell you to put in here so that you reduce the load that this will have on the chassis. And then this lead is point V, I guess. And it's we're on the 50 volt scale, so there's a lot of volts there. It says that we're supposed to take this point, which is C1, which is the output of the video detector, and ground this as well. This become our de facto ground point. We should have like pretty much a blank screen. Yeah, so we've just grounded the output of the IF strip, which is essentially that one, the purple wire, only on the other side of the chassis. And it's marked by one of those Zenith tags. So this is our, well, what we're trying to do, okay, so look at when we grounded that, we have on the 50 volt scale, we are at 10 volts or 9 volts. And this oscillator slug here is the amplitude. So we're trying to adjust it for maximum output. So I should get two hands so I'm not going to crack this tube anymore. Let me do that. All right, so I'm going to carefully turn the slug. I have my left hand on the top of the tube. So now I'm turning it, and we should see a change in value. It says we should adjust this for maximum output. Okay, I think that's the end of it. Going back the other way, clockwise now. Maximum output, right there. Well, I ungrounded the C1. I'll try turning our first slug. It's still 7 bars. It's still 420 hertz off. Well, this did turn, and that surprises me, which is great news. It was, I mean, we turned it quite a ways to get that voltage to come up. Let's fool around with the fine tuning. What would happen if we did that? Oh, nothing that we want, I don't think. I mean, I don't know what it's even supposed to. I don't even know. I'm just fooling around here. I'm not doing anything constructive. Well, I pulled one of the diodes out, and stamped on it is just a Zenith part number. That's not the diode type. So if we look at it in the SAMs, this is it, a 103-131, and it says that a replacement part could be a 1N34AS or 1N34A or an ECG 110. Now I think those are germanium diodes, but this one tests like it's a silicon diode. Yeah, the forward voltage is 719 millivolts, or around there, and that's a silicon diode. So I don't have any germanium diodes anyway, so we're just gonna go ahead and replace them. And I took out both of them, and between the two, yeah, there is a forward resistance on one of the diodes. So it's 890,000 ohms. And yeah, there's quite a difference between these two. Let me show you the other one. Certainly more than what would be the acceptable 2% to make them match on either side of the discriminator. So yeah, they're still diodes, but they're just not matched. And I think they need to be matched. Probably long enough, so that's good. And this is a 1N4148. And let's take a look at it on the multimeter. So I've got 1, 2, 3, 4, 5. I got 5 of these. I'm going to see if I can find 2 that match the best. Okay, so I got actually 2 pairs of diodes that could be besties. So yeah, but they're all actually super close to each other. They could all be fine. I have kind of put together a couple of match sets of 2.2 megs from another discriminator project before, and I'm going to double check that they're close, but I'm going to change the resistors also. The resistors that are in there really are very close to each other. Those 2 that are lifted out, they're about 50,000 ohms apart. And I would say that that's close enough, probably. But since we're here, I just thought I'm going to change them. Why not? And the difference between the 2 of them is 9,000 ohms. So that's 0.5% or something like that. So, okay, we're going to stop obsessing about... We're clipped into our test point W, which is the output of the discriminator we looked at before. There should be less than 1 volt here, and that is 1 volt on the scale, and this is on the minus scale. Yes, so we are looking at a negative 0.4 of a volt, 0.5 of a volt, and well, it's under a volt, so that is an improvement, I guess. We're still not there. So I've got this slug turned as far as counterclockwise, I guess. Yeah, it's right at the stop. I'm surprised that there even is a stop, actually. and it's close. Something's preventing it from. And our other slug here, our other transformer, is our amplitude. So with the other adjustment on the top side we were looking at, well, that's how we get this, and it's not happening. I clipped in to our discriminator. Those are the two bursts on either side of the discriminator, and it looks pretty darn perfect to me. And they're clipped in right here on the common of the two capacitors. So that's good. We should look at our horizontal blanking pulse and burst. And I mean, they're right on top of each other. Well, that other tie point is here. It's off of pin 2 on the burst amp. Right there, pin 2 of the burst amp connected in there. So I don't know, more reading. So I'm just making, just switching between the color bars, which would have a burst signal on it, and one of these other patterns that would not. And I just wanted to show you on the scope what it looks like. So that's color bars. And if I switch it to a black and white signal, a test pattern that doesn't have color, that's that. So you can see when the program material has color in it, in the day anyway, there would be this burst signal present, and it would tell the color killer circuit to leave the color on. And then when it was receiving a black and white signal like this, it would tell the color killer to kill it, make it a black and white. Well, that number there is the speed of the oscillator, the color oscillator. It's 3.57965. And then over here we can see that that trace, that's the horizontal blanking pulse. That's the horizontal frequency. And that's the frequency of the color oscillator. So the oscillator is working fine. Right on, right there where it should be. Well, welcome back to the bottom. This is our color oscillator circuit. So let's just review the key components. That's our crystal. This is the coil we've been adjusting to adjust the frequency of the oscillator to sync up and lock onto the burst. And then this coil here, if you remember from early on, it was just sort of flopping there. But we did still have continuity in the coil. And it looked like where the slug was placed, it was still engaged in the area around the windings. So astonishingly, the slug still turns in this tube, and it seems to work okay doing what it does. This is, you adjust the frequency with this tube, the slug in this tube, this coil, and then you adjust the amplitude for maximum gain. Those are the two adjustments that are available. And when I first saw this, I noticed this, and I thought, how did that happen? That it's like a nick, a gouge, and it's safe. It doesn't go into the winding. And I just was trying to figure out what possibly could have happened to have had that kind of damage. But the coil is fine. And it just dawned on me. I couldn't believe it. So this is kind of like a manufacturing thing that somebody hadn't fully thought through. So this has to be adjusted, and to get it to lock. And the wood cutout on this is not far enough this way to really allow you to get your adjustment tool in here. kind of lines up with that rip in the fiber tube. And I'm 100% certain that somebody had taken a razor blade or diagonal cutters and just cut a notch in that so that they can shove one of these adjustment tools in at an angle. It's flexed at an angle and get it in there and adjust that slug. I'm positive that's what happened. So this was done by somebody else. And if we look on the other side of the coil, on the top of the chassis, yes, there's an adjustment point. But it's also one of these manufacturing coincidences. This support arm for the high voltage cage, deflecting, you're bending the adjustment tool to get it into the coil and into the core. And this one's a little bit easier, but nevertheless not so easy. And as I mentioned, we've got this one turned all the way counterclockwise, and I think it makes it rise in the tube like that. And I'm wondering if there was ever some body that tried to shove a tool in at an angle and crack the core, and then we had to replace the core with something else. And I'm wondering, out loud, if that's the correct core in there. If that slug had been replaced with one that isn't the right material or one that isn't the right length. I'm wondering that. Because it seems like yesterday anyway, when we were trying to get this synced up, it just was very close. It just needed to be a little bit, the tuning of the oscillator needed to just go a little bit slower. This 0.1 microfarad cap, it's in the discriminator circuit that we were looking at yesterday. And it's odd because it's a Sprague orange drop, but there aren't any Sprague orange drops in this chassis. I don't think they even existed at that time. Most of these big coupling caps would be like this. They have like a dull maroon finish or terracotta finish, something like that. And so there's no question in my mind, especially after seeing some of these newer solder and some of these solder cones, we talked about that too, that this has been replaced. No question about it. This goes right into the discriminator circuit. It connects over here to a coil. The coil goes to a resistor, and the resistor goes to the cathode of the 6GH8, which is the reactance tube or the oscillator tube. So I believe that this chassis has had a history of color problems or color sync problems, because changing this exact capacitor in that circuit is one of the strong suggestions by R.L. Goodman in his book. And so this has been chased by somebody. The fact that we had attempted adjustments here or adjustments here, and we have this capacitor replaced. I'm surprised that these were never done. But the resistors that we took out, and including these resistors here, the old resistors, they did not look like 55-year-old resistors. They looked like they were 20-year-old carbon comp resistors. So I have a feeling that the resistors have been changed because they were fairly close. Maybe the diodes have been changed. This has been changed. That's been adjusted. Well, how about that? So from the top, I turned the slug clockwise from the top, and so the direction of travel is correct. But look at what the end of that slug looks like when we got it to this point. So yes, somebody had broken the core. And if I can turn this a little bit more, if we can get this out, so I found a bag of slugs, And this is our Slug that we took out with the chip on it. And I thought we'd try maybe replacing it with something a little bit smaller. It appears to have the same pitch, but as we were trying to tune it, it just felt like it needed to go further. How do you say? Modify it. It was a little bit too big in diameter, so anyway, I installed it. It's shorter, and let's see what happens. We've got our set in current limited mode. We are on color bars. I have no idea what's going to happen when this comes up, so we'll just enjoy it together, I guess. Oh, there we go. Fine tuning. There. Is our fine tuning circuit on or off? Well, I think it's on now. See that jitter in the... Let me widen out. There's jitter in this vertical circuit, and who knows? Okay, so in theory we are... Let's see what happens. Let's go to color bars. We maybe have the fine tuning in the wrong place. There's color in that, so the color killer is not doing the trick. It's probably not tuned properly. All right, so we have black and white color bars, and let's just see if it's our fine tuning that'll allow us to bring it. Nah, we still have our have our rainbow again. All right. Shoot. I'm gonna turn our new Slug Oh, that's how it's supposed to work. All right. Great. And I don't think our tuning slug is all the way at the end. I'm pretty certain it isn't. So I put in a smaller slug. And let's take a look at this. Dial in some fine tuning color. And Jesus, looks good. Looks good, everybody. But we cleaned up our discriminator circuit, replaced the two resistors, they're matched, and the two diodes, they're matched as best we can. We did adjust the amplitude of our 358 oscillator, but we changed the slug. We took the old slug out, and we put a shorter one in there, and it seems to be sufficient to get it to just sort of snap right back in. So what we might do here is shut the set off. It's really working well, but it's not quite right yet. So we're still... And then we got that whole tuner thing, and then we got the whole space command thing, and then eventually we'll take everything out. The chassis, the picture tube, everything, all the parts, and we're gonna restore the cabinet and the escutcheon and the plastic things. So, work in progress, but we've got color back. Yay, color!